Had to take a short coffee break. My espresso. So before I get into the last part of this review, mainly dealing with gravity and string theory and modern observation, I just want to briefly explain a little bit about the reason the math is the way it is, because these are some things I kind of had to infer upon when I started studying this, so I could be totally wrong, but this is just the way I see it. So in this equation, for example, with kinetic energy, I compared it to potential energy and to why these equations are so different despite they are dealing with energy. One similarity is that the radius isn't squared, which is interesting, and the reason that it's not squared from what I've seen is that it's not going in a circle. It's not going by a revolution where there's a dynamic movement. So while something is rotating, it's also rotating around something else. This is going in one direction. So that's why I would say that the radius isn't being squared, but also that with kinetic energy, when the mass and velocity are being multiplied by half, or just the mass is being multiplied by half, however you view that equation, however you decide to do it. It's the reason because when you throw something in the air, there is a temporary weightlessness that comes to it, because, when you throw something up, it temporarily pauses before going back down, and that's why it's half. That's the way I see it. And then, of course, let me see what other equations where I could clarify some confusion. I already explained why things come in a negative power. Uniform circular acceleration, the radius is not squared. Oh, here we are. I believe the radius isn't squared here is because if it's a uniform circular acceleration, it's already going in a circle. It's already covering like the full diameter of that circle. But more so the inverse law, I did touch upon this before in other PowerPoints. And I want to say that when something is inverse, consider it like a fraction. So for example, the number 3, you may not see it as a fraction, but in things such as geometry or calculus, I think, or other forms of advanced algebra, a whole number is still a fraction because 3 as a whole number could be considered 3 over 1. We don't see the 1 because 3 in and of itself is a whole number. However, the inversion of that would be 1 over 3. So when you inverse something, you are basically switching the denominator and the numerator. Numerator's on top, denominator's on bottom. And when you square something in these equations, so for example, let me find one. Oh, here we are. So force is mass over second squared, or second per second. It's because the movement is going so fast that you're piling on those seconds. This is just the way I'm seeing the equations. So those are things I wanted to clarify. And again, I apologize for the macrocosm of the universe sun equation not going well. It's not that important right now. I just wanted to touch upon it. So let's get back to discussing the flaws with a Newtonian universe. So as I was saying, Newton kind of saw the universe as everything being held together by gravity. And the reason it's wrong with that is this is kind of pre-quantum era, but at the same time, we have proven that the universe is expanding in the farther regions. So our region is more or less we don't see things within our system going farther away, but in the farther regions of the universe, we do see this. And these regions are moving away where their distance is proportional to the rate at which they are leaving us. So you would have an potentially inverse relation there. I'm not going to get too into it until I actually put up the formulas in my next review. But now I want to discuss gravity, because gravity is actually far more important than we think it is. So according to string theory, gravity, much as any other particle, does have a string wavelength identity to it. And this is called the graviton. So all particles, according to this theory, possess tension, wavelength, energy, and of course spatial definition. Strings are energy, but they do have this spatial consistency to them where you can bend them and shape them. They're not just pinpoints or little dots, because dots don't have spatial definition. on a quantum level. But despite it being a particle, or as it theorized is to, it is the weakest force. And by this, I mean it can be overcome. So me jumping up and down defies gravity. For a moment, I pause. You don't really register it like that, but you can't overcome gravity. A magnetism overcomes gravity. So if I were to pick up a paper clip with a magnet, yeah, it's defying gravity. That is why it's the weakest force. And it's been calculated by string theorists such as Brian Greene, for example, who I'm still a huge fan of, may possess zero mass, much like a photon, but has a 2 spin. And a spin is essentially, as I said before, as an angular momentum in which the particle moves. But also you could view it this way as when you rotate a particle, a spin is how many times you could rotate that particle around before seeing its face again, or seeing the same composition of it again. So it would be a 2 spin. And this gravity affects all matter and energy within the universe equally. So, and the interesting thing about gravity, considering it is so weak and we do not necessarily interact with it the way we interact with other particles or fields such as light, for example, or the nuclear force. Gravity may in fact be penetrating string dimensions, as it's minute, and it's in fact nearly untraceable amounts of energy are not found or conserved when kinetic energy is expelled. And where is this energy going? Well, it could very much well being absorbed by the I'm sorry about that. My other dog Duke is being petted right now. Yes, Duke, you're a good boy. You're a good boy. Let Mama do her review. In fact, this energy is being consumed by the dimensions in the strings, and gravity being the only force that is theoretically able to penetrate these dimensions within the strings of particles is going into that dimension. And if with black holes gravity is so intense it traps in light and other energy, why not the graviton and other string particles, for example? And of course, we're going to get into gravity, the Big Bang. So in order for gravity to exist now and have its effect on mass, it would have had to always have existed. So therefore, gravity, the graviton, did in fact aid in the Big Bang. And some people might say, well, gravity existed over time when mass came about. But that's not at all really plausible. And by mass, I mean like clumps of elements. So nebulas, galaxies, constituent elements such as hydrogen and helium, which would make up stars. But gravity, well, it has an attractive force, has actually the capacity to be a repulsive force, pushing things away. And you might ask how, and I'm going to go and glaze over what I've read. Due to the intense density and temperature of the mix of quarks, the constituent particles that make up atoms, and gluons, the particles that hold neutrons and protons together within the nucleus of an atom, were the Big Bang ingredients, amongst other things, that gravity, in fact, had to push outward. So think of it like a negative pressure within a bottle. So that bottle is holding in, let's say, soda. And that negative energy, that push, is keeping that carbonized liquid in there. Once you open the top, it kind of repulses outward. It all comes out. And think of gravity like that for a moment. But at the same time, because every particles were somewhat uniform, there was this supersymmetry going on. There was no way to really get there until the Higgs boson field kind of created a sloping mechanism where particles were like going up and down, up, stopping, up, down, stop. So things were kind of going up and down, freezing for a moment, gaining momentum. Particles were beginning to have their own identity as the Higgs boson field interacted and gave them all their unique mass, their own unique identity, the graviton being one of them, and that repulsive force pushed outward. And this goes in with inflation theory. As I said before, the early universe was inflating, standing still, conserving energy before pushing outward, and gravity taking its own identity and playing its part. So as the universe cooled, the quarks and gluons, as I said, would form constituent atoms of elements. Gravity took on a new form of being attractive, pulling clumps of atoms together to form matter. And lastly, gravity as a string. If gravity is indeed ruled by the graviton with its calculated mass and spin, it could very well, as I said, be used to penetrate another dimension. which could give us access to the theorized strings that make up space-time fabric of our cosmos and perhaps many others. So the concept of looking into space, of looking into time, as they are in fact one and the same, of looking into the possibility of other universes, other parallel dimensions, the space between dimensions. What's really going on? Gravity, in fact, is playing a major role. It was there in the Big Bang. It was one of the driving forces. It's a driving force in black holes. It's a driving force in everything. It interacts with everything. So what gravity essentially is? It is a mysterious force that has made a lot of what we know it nowadays to be plausible in our universe. So hang on for next time for chapter 3 and maybe 4 of Cosmology for the Curious. And I would love your input. I'm not a scientist. I'm just a science enthusiast, and I really want to know what you think about gravity and overall how its particle constituent can in fact change the way we view the universe.